Hello everyone, we are Team Interstellar and our innovation focuses on India's self-reliance in space technology. Interstellar addresses these problems of space technology. Right now, Earth's orbit is getting crowded. Already 36,000 pieces of debris larger than 10 centimeter are flying at 27,000 km per hour. If this is not addressed by 2030, there will be over 1 lakh satellites. There are many examples of space debris. In 2009, two satellites, Iridium 33, an American communications satellite, and Cosmos 2251, a defunct Russian satellite, collided in orbit at a speed that single crash created over 2,000 new pieces of debris spreading across multiple orbital paths. In 2023, SpaceX Starlink satellites narrowly escaped collision more than 1,000 times in a year. These incidents show one thing: our orbit is turning into a traffic jam of space junk, and when two satellites collide, they create thousands more debris pieces, a chain reaction called Kessler Syndrome. The worst part: losing communication with astronaut or shutting down navigation satellites because of one collision. The problem is current system NASA, ESA, even ISRO are reactive. They warn after danger is detected, not before. There's no unified system that can predict both collision and communication failures in advance. That's exactly what we did. We created Interstellar, a proactive AI system that does not wait for a failure, it stops before it happens. Think of our solution like a traffic signal, but for a space. It has two main parts. DebX. It works like traffic signal in space. It predicts collision up to 72 hours in advance using real satellite from Celestrak, ISRO, ESA and NOAA. It runs machine learning models like LSTM and Kalman filter to see if two objects will come too close. Then it suggests actions like adjusting orbit or deploying drag sail to avoid impact. Now the second part is Safe Leo. This one keeps the communication link alive. It predicts communication blackout using STAGNOS and DSN, Deep Space Network dataset. It works like WhatsApp group in a space. Even if one satellite goes silent due to space weather or inferences, it instantly reroutes the message through another satellite. So, even in a debris-heavy zone, astronaut and satellites never lose contact. Now let's see this system architecture. This diagram maps out the entire backend and front-end ecosystem of the interstellar system. You can see here client platform that can use Apple, Android, Windows, Linux, all supported via React and Tailwind. User roles: who can use? Astronaut, mission control system, satellite operator, researchers, admins. And the core services we have provided are AI/ML and simulation engine that for debris prediction and routing. Second, cloud and database infrastructure. Here stores orbital data, logs and analytics, and we have provided authorization and security. It manages access levels. Third, we have provided monitoring and analytics. These track system health and performance. The fourth one is space data APIs. We have pulled real-time orbital and weather data from multiple sources. Now the communication services we are providing enable satellite to satellite and astronaut messaging. And we have also provided restriction functions like It can be used as a freemium based authorization based system. Now let's move to the next slide, that is technology stack, what we have used to make this project. We build a working demo using real-world dataset, not stimulated data. The front end is made with React and CGM.js to create a live 3D map of Earth's orbit. You can see satellite, debris zone, and coverage area moving in real time. The backend runs on Fast API and Python using libraries like SGP4, Skyfield, and Polyastro for orbital tracking. AI models are trained with TensorFlow and PyTorch, and data is stored in PostGIS and PostgreSQL for SAPtual queries. Everything is containerized using Docker and can easily scale on cloud. Now, what this UI navigation flowchart shows, basically, this is the UI of our app. So, this shows how users interact with the system. Start with login and authentication. If validation fails, demo mode with limited access like static prediction, sample orbit. If the validation succeeds, full access to real-time alerts, orbital and risk views, satellite health, live 3D map, AI prediction strategies for astronaut, and end with access to AI-driven decision support. Now let me show you the live demo. So here what we have made, you can see here, firstly here we have categorized how many satellites are present in LEO, MEO and GEO. So you can see for MEO we have 24 and for GEO right now we have 1, and for LEO right now it is 0, but as the time pass or surprise it increase or decrease. And here we have shown with our Earth what and with our satellite surrounding what are the closest 10 satellites that are present. You can see here as there are so many. There is a Starlink here, I will show you. There is a Starlink. There is this TJS. It is right now on geo level. So you can see here. And here we are, calculating debris and conjunction and com calculation, basically communication. How much far it is, or is it colliding or not, or what maneuvers we can do, like we should move forward, backward, or we should use sail or drag methods. Now you can see here when I click here at the Starlink, we will see like a yellow line, there it goes, so it shows it is moving, how we can avoid it, and in which direction we have to move. So there you have shown it, seen it like there. So let's again go to the main page. So basically what it is does, here it is debris and A, and for future we are adding here for weather forecasting and solar wind and everything what is left here. So basically this is the basic model, you can say, we have developed. You can see, let me show you the one geo and 2. We can see geo and above. Yeah, here this is TJS13. Let's see from the view. Okay, here it is. So you can see, I think, yeah. So this is what we have built. This is the prototype we have built for our project for the Interstellar. Now let's move to the next part, feasibility and viability. Technically, our system is completely achievable using existing open source tools and dataset. We are using technologies like Python, TensorFlow, LSTM, GRU, Kalman filter, and Monte Carlo simulations, the same method used in current space research. India already has all required dataset through ISRO, Netra project, Aditya L1 space weather mission, and NAV-IC GSAT log, so we don't depend on any foreign data. Our architecture is modular. We can start with debris prediction, then add communication routing, and later extend to full mitigation. Now let's move to the operational feasibility of our Interstellar. Operationally, it is very simple to deploy. It is containerized using Docker and Kubernetes, which means it can run on ISRO infrastructure or cloud platforms. The dashboard is built for ease of use with real-time alerts, simple control and minimum training needed because it is open source and CI/CD based. Update can be rolled out quickly without redesigning the system. Now, what is the strategic viability? This is the first indigenous AI driven dual space safety system. No one, not NASA, ESA, or ISRO, currently offers this unified architecture combining collision protection, communication resilience, and AI routing. Stellar reduces India's dependence on foreign systems, strengthen data sovereignty, and contribute directly to Atmanirbhar Bharat in space technology. It can also boost India's space tech export and startup ecosystem. Now let's see the business model of our Interstellar. The global space debris and satellite safety market is expected to cross 20 billion by 2030. Our target users include ISRO, InSpace, DRDO, private satellite startups, and telecom operators. We will use a subscription based dashboard and API model offering B2B contract with aerospace player and premium access for universities. Now, long-term stellar. For long-term use, Interstellar can expand to global client, becoming a part of space traffic management and secure communication network worldwide. Now let's see what will be the impact of our project Interstellar. So here is the graph. You can see basically how after 2010 there is a sharp increase in the space debris. Now let's see what is the primary and secondary factor or impact of our project on the audiences. The impact is both national and global. For India, it strengthens Amrit Bharat, boosts our space tech capability and promote data independence. For ISRO, InSpace and DRDO, it ensures safer mission, lower collision risk and reliable astronaut communication. For private satellite operators like OneWeb India, Agnikul or Skyroot, it reduces downtime and extends satellite lifespan. And globally, Interstellar can be affordable Indian alternative for debris management and space traffic control. Beyond space, it supports disaster and rural communication and builds next generation AI expertise in India. Now, let's conclude our interstellar project. So this is what we have made. So these are the references from where we have extracted the data set, and these are also few research papers from which we have gone through which will be the best model to use in our project. So yeah, so let me conclude myself. In 2009, the Iridium and Cosmos satellite collided because no system saw it coming. Interstellar changes that. It's world first proactive AI that can see danger before it happens, keeping satellite astronauts and communication safe. This is not just a space solution, it's India showing the world what's possible when innovation meets purpose. While other monitor, we predict and prevent. That's our biggest innovation. Thank you so much.